Hello all. Today we have another example for the analysis of the placement of the rigid frame structure. This example we going to analyze the steel rigid frame that's shown here. This frame has the support of pin at A and the roller at B. Under application of the force, this frame gonna deform and they requires us to determine the displacement at B and also at C. This steel frame it has two columns and one beam. All of them have the equal E and I. That means this frame gonna have a constant EI or a constant fractional rigidity. Okay, and we will use the EI to compute the magnitude of the horizontal displacement and at B and C later. Now, before we start, I think by the method of virtual work, the first step, we're going to consider the elastic curve of the frame and the virtual work equation. Virtual work equation. Under the application of 40 kilonewton, the pin would move. Okay, since the pin prevent the movement in the horizontal and the vertical, that means the displacement at A in the horizontal direction equal to the displacement at A in the vertical direction, and it's going to be 0. Okay. However, the rotation can occur here. Okay. The rotation here can occur. It's allow rotation for the pin. And under the application of 40 kilonewton, for sure, this point supposed to move to somewhere here. Okay, and due to this kind of movement and due to the moment that may occur in the column AC, this part of the frame should be curved like this, and we may have this as the zeta sub A. When the column AC curve like that, what happened is this is the rigid frame. So the joint C, when it's moved to C palm, okay, is going to maintain its perpendicular between the column and the beam. And let the displacement from C to C palm, let's we call it V sub C H. Okay, this is going to be the vertical direction. At this point, what we have is the rotation of the joint C in the beam and in the column. They are going to be equal. Let it be equal zeta sub C. How about the vertical, the displacement at C? Vertical displacement at C is 0 due to very small deformation of columns. Actually, the phi sub dv gonna be 0 because on the column is very small compared to the author displacement. Okay, and then we're going to have this also. And what happened is the D also gonna move in the same amount of C. So if this one is about 1 centimeter, this one supposed to be 1 centimeter. Why? Because the same thing. Because the beam, V sub CH is going to be the displacement as DH due to very small deformation of the beam, this is of the column, this is the beam CD. Okay, and then we have that. And if this occur, what going to be the rotation over here? Yes, over here they're going to have to bend from here to here. And what happened again? The angle at this point will be maintained at perpendicular angle. So this must be like this. And then the rotation here, and here, the rotation from here to here and from here to here, gonna be theta sub d as the unknown. And since this B is the roller, so the displacement at B in the vertical direction gonna be 0. The roller have the reaction B sub y. Okay, so this displacement is 0, and it can move horizontally here, right? So this is going to be V sub B horizontal. And since the reaction at the B is only in the axis of the BD, so the BD have no moment. Let's say M sub BD gonna be 0. So this is gonna be straight line, and it's gonna have the displacement of the column BD like this. Okay, and what we have is this is the V sub B horizontal. So based on what we have, we're going to determine this V sub B horizontal and this V sub C horizontal basis on what they're asking us here. And then we have the virtual work equation. From the virtual work equation, what we have is the external virtual work must be equal to internal virtual work. What it means by this, if we like to use the method of virtual work, we're going to apply a unit load to determine the displacement in the horizontal direction. Okay, first one, they ask us to find at B. So by doing this, it means that we gonna apply the 1.0 force, very small force, into the frame that is in equilibrium. Okay, when this happen, is the V sub BH is the real displacement times the assumed 1.0 force. So this is gonna be work. Okay, the displacement time the unit force. So this is going to be the virtual force V sub BH. and this is gonna be equal to integration of what? This 1 unit force gonna produce the moment in every segment of the frame. Let's call it M sub BH. Okay. The M sub BH also gonna produce the virtual work when this time the deformation of the frame. The moment supposed to time the slope, okay, to produce the work. And what is going to be the change of slope of the frame? We have the elastic beam theory of d square v by dx square equal to m over ei. Okay, and based on the mathematics, this is gonna be d by dx of dv by dx, and it's going to equal to m over ei. Okay, and you may have this is as the d theta. The small change differential of theta is going to be equal to m over ei dx. And now, if you put that into this equation, this is going to be integration of m sub bh times what? Times m, okay, over ei dx. What is the m? The m gonna be the moment that's occur due to the applied force, due to the 40 kilonewton. Okay, so assume force times the real displacement is the external virtual work. The assumed force produce the bending moment and time the real change in the shape of the frame is going to be the internal virtual work. And again, if we put the 1.0 unit force, this time we like to determine the horizontal displacement at C. So we go to the C and we put the 1.0 force there. This 1.0 force gonna time this real displacement. So what we have is going to be 1.0 times v sub c h, and it's going to be integration of what? Of moment due to the 1 unit force. This is moment at c h. Okay, this is m sub c h. And then again, time the change of d theta. So time m over ei and dx. So we have the virtual work equation as shown here. By the virtual work equation, what next we supposed to do? We're going to determine m sub bh. Okay. We also going to go to determine the m here due to the applied loading, and also we going to determine m sub ch for this. Okay, so next we're going to do what? Second, determine the equation of bending moment. That's going to be m and what? M sub bh. Okay, and m sub ch. Okay, that is our next step. Before we can go to determine the equation, okay, the equation, we're going to set the required coordinate of each member or segment each segment of the frame. Okay, and they're going to go by the same way when we determine this m, all of the coordinate is going to be the same. Let me set this one as the x1, okay, and this one as the x2, and this one is the x3. Actually, we can set anything you like, but when you set this, every setup x1, x2, and x3 for every cases must be the same. They must be the same. Okay, and then now we are ready to determine this one. So what next then? We draw the free body diagrams and determine reactions and the required more bending moment. Okay, the first one, we start by consider this, because the M gonna involve these two equations. Now let me just take this support out before we can draw the free body diagram. We're supposed to take the support out, and then we can put the reaction into this. What happened for the first one? When the 40 kilonewton apply here, okay, if you take the moment here, you may see the 40 kilonewton will rotate in the clockwise direction, and the force here will rotate in the opposite. So let's say this is going to be B sub y gonna rotate counterclockwise, this is going to rotate clockwise, and if this B sub y is up, so there is no vertical force, so the A sub y gonna be down, and the 40 kilonewton to the right. So for this one, this is gonna be A sub x. Okay, and now we may use the equation of equilibrium. Summation of the moment about A equal to 0, and then you have the B sub y is like this. So the B sub y gonna have the moment arm from here to here of 2.4, and then the 40 gonna rotate in opposite direction equal to 40, and then you got to times 40 by 3. Now you get your B sub y equal to 120 divided by 2.4. So your B sub y gonna be equal to 50 kilonewton. Okay, this is gonna be 50 kilonewton. And now coming back here, if you do the summation of x sub x equal to 0, this one is positive in this direction, so the A sub x equal to 40 kilonewton, like this. And also, if you do the summation of f sub y equal to 0, this is downward. Let's say downward is positive, so your A sub y gonna be 50 kilonewton. So you underscore it to make it. This is gonna be 50 kilonewton. This is gonna be 40 kilonewton. Now again, you draw the free body diagram of each segment. this one, the first one is for the x1, and this for the x3, and maybe this for the x2. Okay, and you may have this is x1, this is x2, and let's say this is x2, this is x3. And when you set up the direction, when you set up the direction of the moment, this setup gonna use for all of the small m moment. Okay, and if you have this one, summation of moment equal to 0, and then you get the force here of 50 kilonewton, and then you get the force here of 40 kilonewton. Okay, this is 40 kilonewton, and this is x1. So if you summation of moment equal to 0 here, you're gonna have m1. Okay, in this direction is positive, and 40 gonna be in opposite direction, so it's gonna equal to 40 x1. This is the first one, and this one is 50 kilonewton. And if you take the moment here, you're going to have the moment arm of x2. And let me set this is going to be the m2, summation of moment equal to 0. So your m2 is going to be equal to 50, okay, and times x2. And the last one we have this is the b sub y here. And let's put this one as the m3, summation of moment equal to 0. So m3 is 0. Okay, that is for the moment due to the 40 kilonewton force. And then we come to this. For this one, we have 1 kilonewton here. So by this one, we may have this one as the a sub x, and this one as the b sub y, and also this one as the a sub y. If you're doing something like this, you just set up summation of moment m sub a equal to 0. Take moment about here, so b sub y again. Rotate this as a positive. Your b sub y gonna time 3. And then what we have is there is no force, so you got b sub y equal to 0. And then if you do summation of f sub y equal to 0, a sub y gonna be 0. And then if you do the summation of x sub x equal to 0, you got the a sub x equal to 1.2. So this a sub x is going to be equal to 1. And now we are ready to draw the free body diagram of each piece of this frame. Okay, this is x1, x2 and x3, and you're going to use the same. This is 1, this is m sub h bh bh1, this is m sub bh3, this is going to be m sub bh2 in the same direction that you set up here. And what happened is this one, that is going to be 1. If you summation of the moment here, summation of moment equal to 0. So this is in opposite direction. So this one is going to equal to x1. How about this one? This one have no force here, but it has the 1.0 here. So if you take moment here, this 1.0 gonna have this 3 meter 3 meter. This 3 meter moment arm. So summation of moment equal to 0. This is going to be 3. And again, for this is going to be 1.0 again. And summation of moment equal to 0. M sub xt going to be here. And this is going to rotate in this direction. It's going to be 1 times x3. So this one going to x3. Okay, that is the next one. The last one, if you can consider here closely, this one unit assume force is in the same direction as this 40 kilonewton. So what we have is going to be, this is going to be equal to m divided by 40. If this m divided by 40, so we're going to have m sub c h1 equal to, you may put this one, 40 x1 divided by 40. So this is going to be equal to x1. Make it clear on this. And it's going to have this direction also. Okay. And this one, x3, you're going to have m sub c ht equal to 0. The same direction here. And for this, m sub c h2 going to be 50x2. And then must divide it by 40. So you have this for 5x2 divided by 4. Now, that's, you have all the required moment, okay, here. And one of the best way to help you to put all this equation into this virtual work equation by using the table. Okay, we're going to draw the table. We're going to have 1, 2, 3, and 4. What we have is, we have the segment. Just put this one. This is the segment. What we have is A to C. So segment AC. From D to C. DC. And from B to D. B, D. And also you have the length. Okay. This one from 0 to 3 meter. And this one from 0 to 2.4. And this one from 0 to 3. Okay, and then what we have is the equation of the moment, m kilonewton meter. And what we have is, this is 40x1. This is going to be 50x2. And this is 0. And you have this m sub bh. That is going to be x1. This is going to be 3. And this is going to be x3. And the last one you may have is m sub ch. What we have is, this is x1, and this is going to be 5 over 4 x2, and the last one is 0. Now we are ready for the third step. We determine the displacement displacement. What we have, displacement is going to be V sub B H and V sub C H, two of them, based on what we have in the table. Okay, V sub B H gonna be, the first one is gonna be, this is the green one, it's gonna be this one and this one, V sub B H. Okay, that means we're going to integration of 40 x1 and times x1 and now dx1 over ei, and you integrate it from 0 to 3, and next plus here. Okay, integrate from 0 to 2.4 of 50 x2, and this is gonna time 3 and dx3 over ei, and the last one here is gonna be 0 times x3, so that's gonna pass 0. Okay, now we have 40 x1 square, so it's gonna be 40 x1 cube divided by 3, and you integrate from 0 to 3 and divided by ei, so we just put this one out, 1 over ei here because they are equal, and then you plus this one gonna be 150 x2, so it's gonna be 150 x2 square divided by 2, and then you integrate it from 0 to 2.0 and then plus 0. Okay, you put everything in your calculator. You may have the first one 40 times 3 cube divided by 3, so it's going to be 40 times 9, it's going to be 360. This is going to be 75 times 2.4 square. Okay, and then you have this as the sum of 360 and 432, that is going to be 792 divided by ei, and it's positive, that means it's going to be in this direction. Okay, and then you may compute the magnitude of this is going to be 492 divided by 210 power 6 kilonewton per meter square, and the I going to be 60 10 minus 6 meter power 4, so this cut this, and then you may get this of 0.066 meter, or it's going to be 66 millimeter in this direction, as you may have. So this is going to be equal to 66 millimeter. Okay, and the other one you compute V sub CH, so V sub CH gonna be, that's gonna be the time of this and this, this and this, this and this. Okay, now we have integration of 0 to 3, and we have 40x1 times x1, 40x1, and you're gonna time it by x1 and the x1 over ei. That is the first term, and then we plus this next integration of 0 to 2.4, and we have 50 x2, and it's gonna time this one 5/4 x2 and dx2 over ei, and the last one plus 0. Now if you do the equation at the same as before, you will get this of 648 divided by ei, and since it is positive, the same direction as this one. Okay, and then if you put everything, it's gonna be this one divided by 260. You may get this one of 0.054 meter, or it's going to be 54 millimeter, and that's it. It's going to be in this direction. Okay, and it's going to be very easy. This one going to be 54 millimeter, and also this one, this is V sub BH is going to be 54 millimeter since this one. Okay, and for the slope, you got to determine them by putting the 1 unit moment to point A, to point C, to point D, even to point B if you like. Okay, this one also gonna have of theta sub B, and I believe these two gonna be equal. Okay, that is the end of the demonstration of showing the displacement of the frame based on the unit load method, or you may call it the moment method of virtual work. Okay, that's it.